be on line spectra and the hydrogen atom. Um, and by the end of the lesson, you should be able to relate the emission spectrum of an element to its discrete energy levels. This statement will make much more sense at the end of the lesson. Okay, so this visual that you see, is Niels Bohr's planetary model of the atom that he proposed in 1913. In this, you have your nucleus at the center, just like you would have the sun at the center of the solar system, right? And in that nucleus, you have your protons, you have your neutrons. And then around it, you have your energy levels. So here, you've got energy level n equals 1, which is the lowest energy level, closest to the nucleus, also known as the ground level. Then you have energy level 2, a little bit further away, 3 is further, 4 is even further. Bohr proposed that electrons only move in specific energy levels. They do not exist in between levels, but only on them. So, how does this relate to light? Light is a form of energy, right? When light falls upon an atom, that atom can absorb energy, thus allowing the electron to jump from this lower energy level, where it likes to be, where it's stable, and get energized and jump up to a higher level. Now this atom is considered to be in its excited state. And whatever jumps up must fall back down. So that's what we see here. The electron drops back down to the ground state, to a lower energy level. But what happens to that energy? Energy cannot be created, it cannot be destroyed. So if the electron lost its energy, that energy must have gone somewhere. So in this case, it comes out in the form of light. So here we see that if the energy dropped a great distance from a much higher level to a lower level, a lot of energy, a high energy photon is emitted. If the electron drops only a little bit, then a low energy photon is emitted. Similarly here, if a high energy photon is absorbed, the electron jumps a lot. If a low energy photon is absorbed, then the electron is able to jump up only a little bit. So here we see atoms absorb energy to allow its electrons to go to a high energy orbit, and then when the electron jumps back down, the atom radiates energy or emits energy. All right, so we'll skip this. Oh, so all electromagnetic radiation travels at the speed of light, meaning everything that you've seen on the electromagnetic spectrum moves at this speed, right? That's 3 with 8 zeros after it. That's how many meters per second it moves. That's, I think, 30 million meters per second. So C is constant. For any form of light, C is constant. And we see here this equation that speed of light is equal to frequency times wavelength, right? So that means if the frequency is increased, the wavelength must be decreased. If the frequency is low, the wavelength must be large. So frequency and wavelength are inversely proportional. That's the relationship. We can visualize that here. Over here, we've got the electromagnetic spectrum. We know which side has more energy, which is the more energetic side. Why? Because radio waves are around us all the time. Microwaves, they're pretty safe. Infrared, pretty safe. But UV light, ultraviolet, we have to put on sunscreen to protect ourselves from that. X-rays, pretty dangerous, right? An X-ray technician wears protective gear all the time. Gamma rays can destroy, can have a lot of destructive force. They're emitted by dying stars. So as you can see, as we head in this direction, is this working? Oh. As we go in this direction, the electromagnetic radiation gets more dangerous or you could also say more energetic, higher in energy. We also see that on this low energy side, we have, so this side is uh, low energy. This side is high energy. You might not be able to see that. And you might not be able to read that. Okay, so, and if we compare wavelengths, this side clearly has fairly long wavelengths compared to this side has very short wavelengths. So from there, we can see that long wavelengths are related to low energy, right? Short wavelengths related to high energy. And then frequency is the last thing we need to look at. Here, we see low frequency, right? It's some slow, languid waves. On the left side over here, we see very frequent waves. So we see that frequency is related to energy. Higher energy means higher frequency. And low energy is related to low frequency. All right, what else do we need to know here? You need to know how colors of the rainbow, right, their relative energies. So the way you know that, red over here, red is right next to infrared, right? Infrared we know is safe. Infrared is less than red. So red is on the safer, lower energy side. Ultraviolet is more than violet. UV we know is not safe. It has highly energetic. It's energetic enough to damage your skin, right? Enough that you need sunscreen. So UV is on the more energetic side. So just a bit more energetic than violet. So in the visible region, red has the least energy, violet has the most energy. So here, how do we figure this out? We just Roy G Biv, right? This is the order of the colors in the rainbow from highest energy to lowest energy. So anytime you see a question like this, okay, what color of light has the longest wavelength? Immediately translate that to energies. Are we talking about high energy or low energy? So long wavelengths, that's low energy. So we're looking for which of these colors have the lowest energy. And we said red is on the lowest energy side. So the answer is going to be red. Okay. See, I'm going to give you guys a chance to try this. Hit pause and then press play. Okay. Longest wavelength. Right over here. Microwaves, longest wavelength. Shortest, you can tell visually. Gamma rays. Greatest frequency. Gamma rays. Lowest frequency. Microwaves. Correlation between wavelength and frequency. It's inversely related. Okay, so let's talk about the spectrum of light. You may or may not know, but white light isn't actually just white light. White light is all the colors of the rainbow, just following the same path, and that's when they look white. But you can take a prism and diffract, spread apart those frequencies that are in there. The light bends, and then you can see a continuous spectrum of colors. We see white light is not actually just white, it's red to orange, yellow, green, blue, indigo, violet. The same thing happens when you see a rainbow, right? The droplets in the sky, in the air, will bend light enough that it'll spread out and you can see this. So here's some terminology you need to know. A continuous spectrum, right? Which is something you would see from the sun or a household light bulb. It contains every wavelength of light in the visible spectrum, right? We see there's no gaps. There's no gaps at all. It's continuous, as opposed to line spectra, where it's not continuous. There's either lines or gaps that correspond to wavelengths of specific energy. Right, so um, every element can have its own absorption spectrum. It has its own emission spectra. It's like a fingerprint for that element, right? Hydrogen will produce lines at specific frequencies that would identify it as a spectrum for hydrogen. Same thing for helium. Helium would have its own lines in different places. And you can see here how absorption spectrum and emission spectrum are related. The lines that are missing, that were absorbed in the absorption spectrum, were released, are the same as the ones that are released in the emission spectrum. It lines up. The only difference is in the absorption spectrum, where there was originally a continuous spectrum and the element removed some. The element absorbed some lines away, and you were left seeing what is left here. In an emission spectrum, there's no initial source of light, but the element releases certain frequencies of light, so you see just those colors. So how are they formed? Oh, actually, before that, here are some examples of the unique atomic line spectrum for some elements. And if I look at a light bulb full of hydrogen gas, I won't see all these colors with my naked eye. I'll see, I believe I'll see a pink. But if I put on diffraction glasses, the glasses will spread out each frequency, it will bend the light, and then I will see these three colors separately, right? And these, the presence of these three wavelengths of light, these three frequencies of light, tell me that the substance that I'm looking at is hydrogen. Similarly for helium, all right? These specific lines tell me that these are emission spectrums for helium, right? It's releasing these lines. How does this work? When a gas of a single element is excited and starts to grow and glow, only certain wavelengths of light appear. Because when those elements are excited and those electrons fall back down to the ground state, they can release visible light. They can release UV and IR radiation. So here we see, say I have a light bulb, I plug it into the outlet. Energy is absorbed. All the electrons will jump up to excited states. If it jumps up to level 6 and energy level 6 and falls back to energy level 2, purple light will be emitted. If it jumps up to 5 and it falls back down, that's slightly less energy, right? So the slightly less energetic blue will be released. If it's only falling from level 3 to level 2, that's even less energy. So the less energetic red light is released. So how do emission spectrums versus absorption spectrums work? So we can see here, in an absorption spectra, there is a source of light, right? There's a source that produces a continuous spectrum, and it passes through the sample, but the sample the sample absorbs certain frequencies that are specific to what it needs for its electrons to get excited. And those frequencies it absorbs, you see they are now missing from the light that's passed through, right? So this is the absorption spectrum. In an emission spectrum, there's no original light source. There's a energy source that excites, so like say electrical current in a light bulb, it excites the sample, and then as the electrons in that sample fall back down to lower energy, it releases light. Depending on what the gaps are between energy levels, you'll see specific frequencies of light being released. So here, this question, here's an emission spectrum for some unknown element A, another one for some unknown element B. The question asks, which of these spectrums represent a compound that contains both elements A and B? How do you check that? You look at the lines for A and you see is there any that match up? Okay, so we know right away that this cannot be the answer, and this cannot be the answer either, because the lines for A are not there. Okay, let's check emission spectrum for B. That matches up. So the answer is this one. All right. So let's review. The lowest energy level for an atom is its ground state. An atom, when it gains energy, will jump up to its excited state, but the electrons don't stay there for long. It will fall back down. And you see the specific gap between energy levels. For different elements, there's a different gap. And those different gaps produce different wavelengths of light when the electrons drop. Forgive my terrible jokes. Okay, so here, just a visual, you have an excited lithium atom, right? It's full of energy, but it wobbles on down, loses its energy, and that energy is released as a photon of red light, and now that lithium atom is stable in its low energy state. All right, so here again is a representation of the different energy levels of an element, right? An electron can be excited from this first level up, but there's many ways to come back down. How many different ways can we come back down? Let's see. Okay. Right, so anywhere from energy level 4, you can go to 3, 2, 1. From energy level 3, you can go to 2, you can go to 1. So every configuration, every way to come down is related to a specific amount of energy, and that amount of energy is related to a specific color of light, and that color is what shows up in the emission spectrum for that element. So here, which arrow represents the smallest energy change? It's actually this, 4 to 3. So you might think 4 to 3 should be the same thing as 2 to 1, right? Because it's just a jump of one level. However, you can see the distance, the energy level gap between 2 and 1 is much bigger than the gap between 4 and 3. Right? This is because energy levels converge as you go higher up. This energy level is far apart, this one is closer, these two are closer. So as you go higher in energy, the energy levels are closer together. So from 4 to 3 is a much smaller drop than from 2 to 1. So the red light represents the smallest energy change. And the biggest drop is from 4 to 1, and that's represented by violet light. Okay, so now we'll talk specifically about the spectrum for hydrogen. Right, so hydrogen is the only element you will need to know specifics about. So looking at the visible region. So here, this is the same thing you've been looking at, just at a different angle. So we've been looking at the visible region, right? Electrons dropping to a specific level, releasing visible light. But hydrogen also has electron drops that could release ultraviolet light. It also has drops in energy that release infrared light. And we see again the convergence, right? Energy level 1 and 2 are very far apart, but then the gaps become smaller and smaller as they converge at higher energy levels. You can see it in this visualization as well. So those 3 series that we just looked at, you probably don't need to know the names, but you do need to know what kind of radiation is released by what type of drop, what type of energy level change. So any energy level changes in hydrogen that ends up at the first level, that's going to release UV light, right? Any drops to 1 releases UV. That's the Lyman series. You don't necessarily need to know them. Any drops to energy level 2 produces visible light. So red through violet. Any drops to 3, that's a much smaller change in energy, only releases infrared light. You cannot see that with your eyes. You need night vision goggles for that. So these three, you have to know. You have to know that a drop to energy level 1 is UV, to 2 is visible, to 3 is infrared. Okay, so answering this question, which of the following statements is correct? All right, so electrons release light when they move from the ground state to an excited state. So let's think about this for a second. If they're moving from the ground state up, are they gaining energy or are they losing energy? They must gain energy to move to a higher energy level, to become excited. So they cannot release light for that. They have to absorb light. All right, let's try B. They release light when they move from excited to ground, right? From excited down to the ground. They go from high energy to low energy, so they lost energy in the form of light. So that's correct. All right, let's try this one. Which transitions correspond to the absorption of a photon? So if a photon is being absorbed, right, light is being absorbed, your electron is going to get excited. So it's going to be any arrows pointing outwards to an outer energy level. So that's C and D. Next, which transition corresponds to the highest energy photon emitted? So if a photon is being emitted, energy is being lost. In that case, your electron must be dropping in energy, right? If energy is being lost, the electron is coming down. So it's either A or B. And it says corresponds to the highest energy photon emitted. So it must be the bigger drop. A. Next, which transition corresponds to the longest wavelength? Again, if you see a wavelength question, turn it into energy. So longest wavelength is the same thing as low energy. Okay, and then a photon is being emitted, energy is being lost, so it must be a drop, an electron dropping an energy level. So that's B. Okay, which transition corresponds to highest frequency photon emitted? High frequency is high energy, and its photon is being emitted, so that must mean energy lost, electrons falling down, but a big drop, so it's going to be A. Okay, so let's try a couple of these. So, which statements are correct for the emission spectrum of hydrogen? Lines converge at higher frequencies. Is that true? Yes, it is true, right? These lines are far apart, and at higher frequencies, meaning higher energy levels, the lines are very close together. Electron transitions to energy level 2 are responsible for visible light. Yep, exactly. Lines are produced when electrons move from low to high. So this is talking about emission spectrum, right? So in emission spectrum, light is coming out, so electrons are losing energy. So no, it's not electrons moving from low to high. It's electrons moving from high to low. All right, let's draw that real quick. So emission spectrums, right? Energy is being lost, it's going out, so your electron must be dropping. So it's going from high to low. Okay, let's try this one. Which statements are correct about the emission spectrum of hydrogen in the visible region? Red line has a lower energy than blue line. Yes, red has less energy than blue. Lines converge at longer wavelength. Lines converge at higher energy, and longer wavelength is not higher energy, so that's not true. Frequency of blue is greater than frequency of red. Yeah, blue has more energy than red. Okay, let's try this one. Which of these is correct for the line spectrum of hydrogen? Line M has higher energy than line N. Let's see. So let's just figure out which way is more energy. Whichever side the conversion is happening, that's where it's more energy. So high energy is on this side. So line M is not higher energy than N because line M is on this side. Line N has lower frequency than M. That's also not correct because if this has more energy, it has high frequency. Okay, does line M have longer wavelength than N? Yes, because it has less energy, so it's longer wavelength. So the answer is C. All right, just a couple more. UV has shorter wavelength than infrared. Actually, I think you guys can do this on your own, so I'm just going to put the answers. All right, here it's asking about an electron transition with the highest energy in the emission spectrum. So an emission spectrum is made when your electrons drop in energy. So it's not A or C. And we're talking about the highest energy transition, so that's B. Okay, this problem, a lot of people leave blank, right? All this is saying is draw the first four energy levels of a hydrogen atom on the axis. Label it n equals 1, 2, 3, and 4. And we see that the y-axis is energy. So the higher your line is, the more energy that is. Right? So this is literally all you have to do. Draw the lines, make sure they're converging at the higher energy levels, and label them. That's the whole point. For 7b, it says to draw electron transitions to n equals 2. Right? So that's plural transitions. You need more than one drop. So and it's in an emission spectrum, so you know you need arrows coming down because energy is being released. So you can draw an arrow coming down from 4 and an arrow coming down from 3. And that's it for that. Okay, electromagnetic waves can transfer energy and carry information. What is that's extra information, right? Sometimes the IB will throw extra information at you for no reason. But all it wants you to do here is state the relationship between the energy of a wave and its wavelength. All you have to do is say either it's inversely proportional, or you can say if one goes up, the other comes down. And that is it for today.